Hey guys, how are you doing? I hope you are doing all well and fine. So in our previous video, we discussed about how to design the toroidal transformer, and we saw some of our calculations and formulas, and our analytical thinking and analysis, and we also saw the simulation. So now in this video, I would be discussing about the toroidal transformer and in general the transformers and inductive loads which can cause the inrush currents. So basically, the toroidal transformer inrush current can cause some of the serious damage if not appropriately managed. Inrush current can cause the circuit breakers to trip and fuses to blow. Additionally, it can cause a complete failure of the transformer itself. So a good looking toroid like this can look like this if inrush current protection is not used properly. So guys, actually the inrush current affects the magnetic property of the core, which causes the energy losses. Therefore, it is beneficial to reduce the initial inrush current, and the best way to do that is to employ the use of inrush current limiters in your application. The job of the inrush current limiters is to reduce the surge of the power that enters the device at switch on at time t equals to 0 actually. They do this by absorbing the heat. The most prominent and the good example of the inrush current protectors or limiters is known as NTC. NTC stands for negative temperature coefficient. So when the transformer is switched on at time t equals to 0, the initial source of power sends a surge of current to the device known as inrush current, which can cause the damage to the power supply. Also, the devices that produce alternating current such as electric motors or transformer as we are talking about can draw several times their steady state current at switch on. Although this additional draw of the inrush often lasts less than half of a normal 60 Hz cycle. That is, this time frame is very small in the matter of few milliseconds. This inrush current occurs in a matter of few milliseconds and lasts only few milliseconds. That is an enough time to cause possible damage to your expensive equipment and to damage the toroid transformer itself. So my friends, the initial current limiter like NTC actually heats itself up while doing this job. So basically this self-heating is caused by the dissipation of excessive power from very high inrush current. Thus the inrush current is dissipated as heat and does not damage the subsequent devices. The NTC actually has the characteristic to decrease its resistance with increasing temperature. As you can see from this graph shown, which enable itself to dissipate and control the inrush current, unlike a normal fixed resistor. As we know that a normal fixed resistor can be connected in series to control the current. That is a current limiting resistor. We all know about that. But that fixed resistor does not have the capability to change its resistance according to the temperature, which NTC has, and NTC is best suited for the inrush current protection. Therefore, guys, so now we will be moving towards the formulas and calculation to see how to calculate and find the best possible NTC from a large list of NTCs available out there in the market that best suits our application requirements. Okay guys, so here we go. So here is the calculation which I have formulated for you guys for sake of ease, and I have done everything all in advance. So let's suppose our input voltage of the transformer primary winding is 400 volt AC and our input current is 1.5 ampere, and our output voltage is required to be 230 volt AC. So this would be a step down transformer, linear step down transformer, and output current of 2.6 ampere. The output current you can formulate according to the transformer equation. With input voltage you will and output voltage you will get the turns ratio, and with the turns ratio you can get the output current, as I already mentioned in my previous video of toroidal transformer designing. And our line frequency is supposed to be 50 hertz. So this is the basic Inrush current graph which you guys already know, and in this video I would be showing you how to select the Ametherms. Ametherm is a renowned company for the NTC's devices manufacturing. Ametherm's NTC selection. So without NTC in our circuit, our sensitive electronic equipment connected at the secondary of the transformer can see this red color high spike of the current. This is known as the inrush current that would be flowing for a very less time period through the devices to be followed at the secondary. But with the Ametherm's inrush current or any other inrush current limiter NTCs, you can see that this peak is reduced significantly, and the rest of the circuitry to be followed is safe. So we would first of all calculate the energy. The inrush current is, we have supposed that it is around 100 times that of the required steady state current, that is 1.5 ampere. That is, our steady state current is 1.5 ampere at the primary. So 100 times, we have assumed that the inrush current is 100 times, so it would be around 100 multiplied by 1.5, 150 ampere. So this would be our maximum inrush current. And the formula for the reactance of the transformer primary is something like this: peak voltage divided by inrush current. And what is the peak voltage of the primary input? So this would be square root 2 times of the 400 volt AC RMS. As we all know that peak is under root 2 times the 400 volt AC RMS, and divided by the inrush current, which is 150 ampere. Therefore it comes out to be 3.77 ohms, the reactance of the primary inductor in primary winding of the transformer. And another formula which we know from the inductor characteristic, that it is 2 pi FL. Therefore as you can see, the inductor is something like, here the frequency would be 50 Hertz, and its inductance will be calculated using this reactance value which we calculated from this equation. So this would be around 0.012 Henry. Now we would calculate our energy in terms of joules, because this energy in joules and this resistance, these are the two values which are needed in our selection of a suitable NTC for our circuit. Therefore energy stored into the inductor is given by 1 upon 2 inductance, 1 upon 2 times inductance times square of inrush current, Therefore we would get 135 joules of energy. Lastly, our minimum resistance calculated, the maximum tolerable inrush current. So we as a designer need to compromise on inrush current. We cannot completely reduce the inrush current to zero, but we would need to compromise to some extent. So we take this to be 2 times. Let the inrush current be maximum 2 times of the input current flowing in our circuit. Therefore it would be 3 ampere. 2 times 1.5 ampere, therefore it would be 3 amperes. Therefore our R minimum would be peak voltage divided by maximum tolerable inrush current. Therefore it would be 189 ohms. So let's check the Ametherm's. Let's check Ametherm's product catalog, and here we can see inrush current data sheets are available with standard inrush currents in their list. As you can see, there are many inrush current protector NTCs. There are many of the NTCs here. So how do we know which would be our suited NTC for our required transformer, primary and secondary, we would get to know with this 135 joules of energy, and with this output current 2.6 ampere of output current. Because this is a 2.6 ampere output current, it is a steady state current, therefore we can assume it to be around about 3 ampere. So let's see what these parameters are. This SSI means steady state current maximum steady state current of the NTC itself, means that the maximum steady state current which NTC can flow through itself is this, that is 30 ampere, 16 ampere, 36 ampere, 40 ampere. But these are very high, these are very big NTCs. We do not need such big NTCs, we need only 3 ampere NTC. Therefore we click on this to sort this through in the ascending order. Therefore let's highlight those with 3 amperes. These are the 3 ampere NTCs. Okay guys, these. And in these 3 ampere NTCs we need the energy to be maximum joules is, we got 135 joules. So we would select 135 joules. And here we can see that maximum here is 220 joules. So this NTC, this one, is the nearest to our application. 3 ampere of steady state current and 220 joules of energy. We can connect, by the way, this NTC 2 times. That is, we can connect 2 of these NTCs in series with each other. In order to increase its energy rating to in order to make it suitable for our application circuitry, we can use this NTC in series fashion 2 times. Therefore this is our NTC to be selected. This is its data sheet here. So I hope guys you understand the calculation and formula. This is very easy and simple. So now let's see what our simulation says about this. Okay, hello guys, quickly going on to the simulation, and I have arranged all this simulation for you guys. Just look this schematics of the simulation carefully, as I have used here this voltage source. This voltage source V1 is the AC voltage source with 400 volt AC, this 400 volt AC RMS, and its equivalent peak is 565.68 volts. That is root 2 times VRS. You can calculate in your calculator manually. And this is our transformer. Its primary is 12 millihenry, as we have calculated here, 12 millihenry. And as our output voltage is 230 volt and secondary, and input is 400 volt AC primary, therefore our turns ratio would be 400 divided 230, 1.74. Therefore with 1.74 turns ratio, we get the secondary inductance to be 3.96 millihenry. You can refer to my previous video of Toroidal Transformer, in which I have described everything in detail about the transformer equation, how to calculate the turns ratio, the primary secondary voltages, primary secondary current, and primary and secondary inductances. Therefore now I have used the switch here. In LT-Spice you can use a switch which is voltage controlled switch. Therefore this voltage source, I have used a pulse source in which it can start from 0 and go up to 1 volt, and it would start with a delay of 50 milliseconds. This is I have here shown here to elaborate you that what is meant by time t equals to 0. When we say at time t equals to 0, this means that this delay has been lapsed. That is, after 50 milliseconds has been lapsed, the switch would turn on. Therefore the time would be started from here, and it is known as time t equals to 0. delay time is 50 millisecond. Okay, rise time is 1 millisecond, and I have set fall time to be equals to 1 millisecond. That is we can that is we can see the rise time and fall time of the uh, switch, that is this switch. And our time period is 10,000 milliseconds, that is 10 seconds. I have used this large 10-second span, 10 second of time span, in order to show you guys that how this inrush current um has its effect on the inductor, because it is of the matter, because without the inrush current protector or inrush current limiter NTC, it is of the matter of seconds. It can take a seconds for the inductor current to go down from a high voltage, high current peak to a steady state current. But with the NTC, the current would relatively and drastically comes to the steady state current level at lesser time interval. Okay, so so these are the schematic, and this resistor I have calculated using the formula, as our output voltage is 230 volt and our output current is required to be 2.6 ampere divide 2.6 ampere. See, using Ohm's law we can get sorry 230 volt divided by 2.6 ampere, 88.46 ohms. Okay, so this is the resistance 88.46 ohm, and this is the secondary inductance. So let's see what our simulation says. Okay, that's it. This glitch which you guys are seeing here, it is not the inrush current or voltage surge. This is the voltage surge you are seeing here. This is because of this switch of the LT spice. I will discuss it later in my later videos, but to show you guys the inrush current, you can see here this span. You guys are seeing here this span is the span of the inrush current. As you can see here, the current is peaking up to 280 amperes. 280 amperes of current it is peaking up to, right? And it is going steadily down without the inrush current protection device. Okay, so now let us use an inrush current protection device, that is NTC. And by the way, the M-Therm do not provide a spice model of the NTC devices, unfortunately. So we would be using another type of NTC manufacturer, and I have already their library in my LT Spice library folder, and I would be using this first one. I don't know its rating or its energy joules or its resistance, but I am just using here it randomly just to show you guys what effect does this simulation have on our output. So I would be using this NTC in series with this source and this transformer primary here. This is the series connection. Okay, it is now connected. Now let's simulate again. As you can see, the simulation process has gone slow because of that device being incorporated into our schematic. And now this is the response of the NTC. With the NTC, as you can see, the current is now peaking up to less ampere, that is 210 ampere, less than 210 ampere, although it was around 280 amperes without NTC. But with NTC it is now peaking up to only 210 amperes. And as you can see guys, that the slope is also steady, and the output current is the inductor current here is now peaking up to only In first cycle it is 195 ampere, in the second cycle it is 191, 188, 180, 175, 188 ampere, 188 ampere, while it was around 280 amperes previously without using NTC. We can see that again in our fourth cycle. Yeah, 186 ampere. Now we can see without NTC, 276 ampere. Okay, so this is it guys. If you like my video, please do like, give a thumbs up, and do like and share my videos within your community and with your friends, and do leave comments on my videos please. If you guys have any questions or anything need to know in detail, I would tell you guys, and or I can make another video on that topic which you want to learn or study from. So this was all about the Inrush current for the inductive loads like toroidal transformer or electric motors. So thank you very much for your patience and take care.